In section 11.6, we're going to talk about something called the natural logarithm. On your calculator, we've been using the button that says log. Underneath of that button was a button that said ln, and that was the natural logarithm. The natural logarithm is the log whose base is e. So up here, the log base e of x, instead we're going to write it as ln x. ln is actually in Greek, which is why it's ln instead of nl for natural logarithm. In example 1, it says, as shown in the diagram, a rope is coiled around a drum and stays in place when the smaller tension T sub s of the rope and the friction mu, that's what this is, it's the Greek letter mu, between the rope and the drum maintain equilibrium. The relationship between the larger tension, T sub L of the drum and the rope, and the smaller tension, T sub S, can be represented by the equation T sub L is equal to T sub S, E raised to the mu times theta, where theta is the measure of the rope in radians. Radians is a unit of measurements we're going to study at the beginning of next semester. When theta is equal to pi and mu is equal to 0.3, the larger tension is 500 pounds of force. When theta is equal to 2 pi and the tension of the smaller tension remains constant, the larger tension is about 1,277.7 pounds of force. What will the larger force be if the rope measures 5 pi and the smaller tension remains constant? So what I'm going to do is I'm going to start with the initial information they gave me, which was that the larger tension was 500 pounds of force, theta was pi, and mu was 0.3. I'm going to solve this equation for the smaller tension. So the first thing I do is this in my calculator, and it's going to give me approximately 2.566. And then I'm going to divide that into 500 to find out that the smaller tension is about 194.83. The second piece of information, if I were to use that, I would actually get approximately this again, because as the problem stated, the smaller tension remains constant. So that information is extraneous. We don't really need to use it. Then the question says, what will the larger force be if the rope measures 5 pi and the small tension remains constant? So if I make the small tension about 194.83, mu is 0.3 for every part of this problem, but this time I make theta 5 pi, and then I just shove this in my calculator, I'm going to find out that the larger tension is about 21,688.04 pounds of force. Oops. To write the word force and it won't let me. Let's move up a little. There we go. Remember the base change formula? The one that said that the log base A of m could be evaluated by doing the log of m divided by the log of A in your calculator. Well, there's no rule about which base you have to convert to. This particular formula, what we do is we change the problem so it has a base of 10. That's because we can plug the base 10 in our calculator. But it turns out that you could also rewrite this as the natural log of m over the natural log of a. As long as the base of the numerator and denominator are the same, you're going to be able to plug this in your calculator. So in this particular problem, I could do the natural log of 291 divided by the natural log of 5. And I'm going to end up with the same answer as if I were to do the log of 291 divided by the log of 5. Either formula is going to give me approximately 3.53. Example 3. I want to solve 7.2 is equal to negative 28.8 natural log of x. I'm going to do this the long way. You could also do this in your calculator by putting this into y1 equals, this into y2 equals, and finding where they intersect. But I'm going to do this algebraic. The way that it works algebraically is I would first divide by negative 28.8. The natural log is the same as the log whose base is e. If I remember that, then I can go rewrite this equation in exponential form. In exponential form, it would be e raised to the 7.2 over negative 28.8 equals x. And then I can just shove this into my calculator, and my calculator spits out approximately 0.78, which is the same answer I should get if I just plug it into my calculator by finding the point of intersection of these two sides. And this is what I would see on my calculator if I graphed those two on my calculator and found the point of intersection. And notice at the bottom, it tells me it's 0.78. Although both of these next two parts of example 4 would probably be best done on the graphing calculator, I'm going to show you how doing them using natural logs would work. In problem A, what we do when we solve this with a log, whether it be a natural log or a regular log, I'm going to write the problem like this. Remember that the rules of algebra say that if you do the same thing to both sides of the equation, it's still the same equation. So as long as I take the natural log of both sides, I should end up with the same thing. Even if I did the log base 10, which I didn't show you in the last section, this problem would work the same way. We have a property of logarithms that say that if you have a exponent, that exponent can be written in front of the log, I could do the same thing on the other side. It would look exactly the same way. Just running out of space here. Then what I would do is, this is something I can shove in my calculator. I would figure out what the natural log of 5 and the natural log of 7 are. The natural log of 5 is about 1.61, and the natural log of 7 is approximately 1.95. So then I would multiply these together. I would get 3.22x is equal to 1.95x plus 1.95. I would subtract 1.95x from both sides to get my x's together. I get 1.27x is equal to 1.95, and then I would divide 1.95 by 1.27, and I get about 1.54. If I did the same thing with the log base 10 instead of the natural log, the log of 5 is about 0.70, and the log of 7 is about 0.85. I would do the same thing. I would multiply. I get 1.4x is equal to 0.85x plus 0.85. I would subtract 0.85x from both sides, and I would get about 0.55x is equal to 0.85, and then I divide 0.85 by 0.55, and I get about 1.55, which is awfully close to what this answer is. However, if you were to just graph this in your calculator and find the point of intersection, you would end up getting about 1.53. I'm going to write that up at the top. Calculator, x would be about 1.53. So all the answers are close to each other. 1.53 is more accurate because the calculator did it for us. Remember that we always get a rounding error when we do it algebraically. All right, we're going to do this again with part B. I want to solve this using a natural logarithm. So what I can do with a natural logarithm is I can start by writing it like this. The exponent becomes the coefficient. Then I would turn those natural logs into decimals. So the natural log of 4 is about 1.39. And the natural log of 12 is about 2.48. Then I would distribute 1.39 x squared minus 1.39 is going to equal 2.48. And then I would add 1.39 to both sides. So 2.48 plus 1.39 is about 3.87. And then I would divide by 1.39. I get 2.78. And then we would square root that answer. And we find out that x is about 1.67. Now, usually when we take the square root, we write plus or minus, but the reason we're not going to write plus or minus is because we can't take the log. Actually, we can't write plus or minus. And the reason I can write plus or minus is because when I plug that in for x and I square it, I'm going to get positive. So technically, the answer is positive or negative 1.67. If instead of using natural log, I use log base 10, algebraically, the problem would work the same way. We would just get some different values. First, I would move that exponent in front of the log. And then I would take the log of 4, which is 0.60, and the log of 12, which is 1.08. And then I would distribute, and I get 0.60x squared minus 0.60 is equal to 1.08. I would add 0.60 to both sides, and I would get 0.60x squared is equal to 1.68. And then I would divide 1.68 by 0.60 and get about 2.8. And you'll notice that's very close to what we got over here, so that when I square root it, I got about 1.67. And remember, it's plus or minus 1.67. And you'll notice if I graph it in my calculator, look, it hits that line twice. So there are two answers, and you would find that those two answers are positive and negative 1.67 approximately. And that is section 11.6 on the natural logarithm.